Welcome to the deep dive. Today we're jumping into something that sounds, well, almost like a contradiction. Rain-powered solar panels, and not just anywhere, but in Phoenix, Arizona, Sunshine Central. It seems counterintuitive, right? Can that actually work?
It's a great question.
Yeah.
And that's exactly what we're here to explore today. We want to
Yeah.
unpack the real feasibility, the tech behind it, and what it practically means for somewhere like Phoenix. We've been digging into the research, looking at the regional energy situation, basically trying to see if this is just a cool idea or something more.
Okay, so let's unpack that. How on earth do solar panels generate power from rain? It feels a bit like magic.
Yeah, it does sound like it. But it's actually pretty ingenious science. The core technology uses something called graphene-coated dye-sensitized solar cells, DSSCs for short. Researchers, primarily in China, developed this. It builds on existing solar tech, but adds a twist.
A twist involving rain?
Exactly. They have this dual energy harvesting thing going on. First, they work like, standard solar cells absorbing sunlight using organic dyes. That's the photovoltaic part. But the graphene coating is key. When raindrops hit it, something else happens.
Okay, I'm listening. What happened?
So rainwater isn't pure H2O, right? It has dissolved salts, which means it carries positive ions. These positive ions interact with the electrons in the graphene layer. It creates a tiny potential difference, basically a voltage. Think of it almost like static electricity, but captured, the triboelectric effect.
Wow, so it's actually pulling energy from the impact or the chemistry of the rain itself.
From the interaction between the ions in the rain and the
Yeah.
graphene, yeah. Now, the efficiency under lab conditions, like simulated rain, is around 6.5%, which, okay, isn't the 20% you might get from top-tier silicon panels in full sun.
Yeah.
But the idea is it provides some power when it's cloudy or raining,
Yeah.
exactly when traditional solar output drops off.
Yeah.
Auxiliary power.
That is clever. But okay, here's the big but for me. Phoenix. You're talking maybe 8 inches of rain a year, average. What specific challenges pop up when you try this in that kind of hot, dry, dusty place?
Yeah, the challenges are significant. You hit the main ones. First, yeah, the low rainfall, 36 rainy days a year on average. So most days, that fancy graphene layer is just sitting there, maybe acting as an anti-reflective coating, not making rain power.
Right.
Second, the heat. It's intense. Panel surface temperatures can easily go over 45 degrees Celsius. That's like 113 Fahrenheit. High heat reduces normal photovoltaic efficiency, maybe 0.5% drop for every degree Celsius over the optimum. Plus, sustained heat can actually degrade the graphene itself through oxidation.
Okay, so heat hits both functions. What about the dust you mentioned?
Huge issue. Phoenix has significant dust. We're talking particulate deposition of maybe 0.8 to 1.2 grams per square meter per day. That dust layer can cut the sunlight reaching the cell by 15, even 20%. So you need frequent cleaning. But cleaning itself, especially abrasive methods, could damage that delicate graphene layer.
Wow, okay. So it's a triple threat. Not enough rain, too much heat, and constant dust interfering. Have they figured out any workarounds?
They're definitely working on it. There have been field trials actually down in Tempe, Arizona. They're experimenting with hybrid systems. So combining these graphene DSSCs with other techs, things like radiative cooling substrates materials that help the panel shed heat passively, especially at night, and hydrophobic nanostructures, basically coatings designed to help repel water and dust, making them sort of self-cleaning.
Ah, interesting. Do those help much?
The initial results look promising. They reported these combined approaches could boost the annual energy yield by something like 11.3%. So, yeah, it helps.
Okay, an 11% boost is something. But what about the bottom line, the economics? Is this tech actually viable for homeowners or businesses in Phoenix anytime soon?
That's where it gets pretty tough right now. For one, electricity prices in Phoenix are relatively low compared to some other places, say 8 to 12 cents per kilowatt hour. And the net metering policies, how you get credited for sending excess power back to the grid, aren't super generous, maybe 60–70% of the retail rate.
So less incentive to produce extra power. How does the cost compare?
Significantly higher. A standard 10-kilowatt graphene DSSC system might cost around $18,750. That's roughly 45% more than a comparable high-quality silicon system. With that higher upfront cost and the other factors, the payback period stretches out maybe 14 years.
14 years. Oof. And how much does the actual rain power contribute to paying that back?
Very little, realistically. The extra energy generated during the monsoon season might only add, say, $10 to maybe $15 a year in value for a typical residential system. It's not nothing, but it hardly justifies the extra upfront cost on its own. Now, things like AI-driven predictive maintenance can help optimize any solar system and improve the return, maybe by 6% or so by cutting downtime. But the core economics for rain power in Phoenix are marginal.
Okay, so economically, it's a long shot for just the power generation. But you mentioned water earlier. Phoenix has major water scarcity issues. Could these panels maybe offer something more than just electricity? Could they help with water?
Now, that is where this technology might find its real niche, its most compelling argument. There are pilot projects, Arizona State University is involved, looking at exactly these water energy synergies. Think about it.
Hmm.
The panel surface is already there. When it does rain, you can collect that runoff.
Ah, rainwater harvesting integrated with the solar panel.
Precisely. 1 square meter of panel could potentially collect around zero point 0.8 liters of water for every millimeter of rain. That water could be used for, say, landscape irrigation right there, or maybe even for evaporative cooling systems to reduce air conditioning load. They're even testing using the solar power generated to run pumps for highly efficient subsurface drip irrigation in nearby agricultural areas. That could cut municipal water use by maybe 30% in those zones.
Okay, that's a potential game changer, using the infrastructure for both power and water collection.
Exactly. And there's another benefit linked to the graphene and those cooling substrates we talked about. They help the panel cool down more effectively at night through radiative cooling, shedding heat to the cold night sky, maybe 5 to 7 degrees Celsius cooler. That lower starting temperature actually boosts the panel's solar efficiency the next day by around 2%. It's a small boost, but it adds up.
So it helps with water and passively boosts its own primary function. What about the bigger environmental picture?
Well, like any solar, it displaces fossil fuels. A large, say 75 megawatt installation could save almost 2,000 metric tons of CO2 per year. And if you combine it with water harvesting and maybe robotic cleaning systems that use minimal water, you could save over 1 million gallons of water annually compared to traditional cleaning methods. The main environmental question mark right now is graphene recycling recovery rates are okay, around 63%, but need improvement. Still, the multifunctional potential is really interesting. So summing it up, what's really fascinating here is that these rain-powered panels in Phoenix are, well, technologically possible, they work, but purely from an economic standpoint for electricity generation. They're marginal right now given the climate and market conditions. Their greatest potential, I think, really lies in those hybrid configuration systems that truly synergize the solar power, the hydro energy capture, however small, and those thermal management and water-saving aspects.
That really shifts the perspective. Maybe the future for renewable energy, particularly in resource-stressed places like Phoenix, isn't just about single-purpose tech. Could it be more about these really integrated systems, systems that cleverly harvest, every single drop of water, every ray of sun, maybe even manage every little temperature fluctuation to maximize overall benefit? Makes you think, doesn't it?